So already we have discussed this while we were discussing vapor pressure, right? So in here what you can see, only the solvent particles are present. What is that we are finding out here? An equation to calculate the molar mass of the solute. So you have the MB here. So you're just going to rearrange your equation so that you will end up here. So this point in temperature, that is the boiling point of the pure solvent, and this point at temperature, that is the elevated boiling point of the solution. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 5 of the chapter solutions. So in the last session we started off with the vapor pressure of solid in liquid solution, and then we discussed what are ideal and non-ideal solutions, and non-ideal solutions having positive and negative deviation as well, right? And then we discuss what are azeotropes and what are minimum boiling azeotropes and maximum boiling azeotropes. So in today's session, we are going to study an important part of this chapter, that is colligative properties. So first we will be discussing what is colligative properties, and then we will be moving on to different colligative properties. So the first one we are going to discuss here is relative lowering of vapor pressure. Then you have elevation in boiling point and depression in freezing point. One more is there, that is osmotic pressure, which we will be studying in the next session, right? So let's begin with what is this colligative property, right? So colligative, it is from a Latin word. Co means together and ligate means to bind, right? So colligative properties are those properties which depend only upon the number of solute particles in a solution irrespective of their nature. So it is very important to remember this definition. What are colligative properties? It is those properties of a solution which only depends upon the number of solute particles. It depends upon the number of solute particles and not on its nature, and not on the nature or number of solvent also. It is only depending upon the number of solute particles which is present and not on their nature, right? So the important colligative properties that we are discussing in this chapter is relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. So all these four in detail we are going to study. There are some equations also relating to that, wherein how we can determine the molar mass of the solute we will be discussing in this chapter, right? So let us begin with the first colligative property, that is relative lowering of vapor pressure. So as you can see here, in this particular container you have only the pure solvent. So already we have discussed this while we were discussing vapor pressure, right? So in here what you can see, only the solvent particles are present, and what will happen, these gas molecules of this liquid present here will exert a pressure on this liquid surface which is called as the vapor pressure, right? So in here only the pure solvent is present here. So what will be, for example, if I am considering this component as A, that is your solvent as A, then the vapor pressure would be P0 A, right? It is of the pure solvent A. There is no other component present here. Now what we are going to do is we are going to add a solute here. For example, we are going to add a solid solute here. Let us assume that it is going to be B. So now in this container you have B as well as A. So you can see the red balls over here are the B, that is a solute. Now once a solute is added, what will happen? The amount or the number of gas molecules getting converted into the gaseous phase will be less. Hence what happens? You can see here, comparing here and here, the number of gas molecules are less. So what happens? Because of that, the vapor pressure will decrease. So this is what is relative lowering of vapor pressure. So why does this lowering of vapor pressure takes place? Once we are adding a solute, right, it will remain in the surface and it will reduce the number of gas molecules which is converting into vapor phase, hence the vapor pressure also decreases. So that is relative lowering of vapor pressure, right? So when a non-volatile solute, now what is this non-volatile solute? Non-volatile means it doesn't get easily evaporated, or else you can also say that it is a solid, right? It is non-volatile, it doesn't get evaporated, is added to a volatile solvent, the vapor pressure decreases, right? So when a solid substance is added to a liquid substance, what is happening is what is written here. What happens? The vapor pressure decreases, as I just discussed now. So the vapor pressure of the solution is always lower than the vapor pressure of the pure solvent, right? Comparing this and this will have more vapor pressure because only the pure solvent is present there. So easily the gas can evaporate. And in here, what is happening? The solute particles are added, hence the vapor pressure decreases. So because of that, this is a solution, right? This is the pure solvent and this is solution. Why? It contains solute as well as solvent. So this is the solution. So in the solution, the vapor pressure will be less, right? The difference in vapor pressure of pure solvent and solution is called as the lowering of vapor pressure. Okay, that is called as a lowering of vapor pressure. How much vapor pressure has been decreased by the addition of the solute? So that we can mention it as delta P. That is the difference, right? So that is P naught A minus PA. P naught A is for the pure solvent A and PA is for the partial pressure of A in the solution. That is partial pressure of solvent in the solution. This is of pure solvent, right? Now, relative lowering in vapor pressure is the ratio of lowering in vapor pressure to the vapor pressure of pure solvent. So, this equation is for the decrease in vapor pressure, how much it has decreased, that you can get it from delta P. Now, what is relative lowering of vapor pressure? Relative means we are relating it to the initial value, right? So, how much changes happened and we are comparing or we are relating it to the initial value, that is the pure solvent, right? So, what will be the relative lowering of vapor pressure? That is the change in vapor pressure, P naught A minus PA divided by P naught A, that is that of the pure solvent. So, this is the equation of relative lowering of vapor pressure. So, this is lowering of vapor pressure and this is relative lowering of vapor pressure. So, I hope that is clear for you. So, how did we get this equation? Now, further going, according to Rolle's law, we have already studied the partial pressure of the gas is directly proportional to its mole fraction, right? So, we have already studied. So, regarding solvent, we are discussing here. So, PA is equal to P naught A into chi A. Right, we have already studied this in Rolle's law. Maybe in 1 and 2 we have studied. So, P1 is equal to P1 naught into chi 1. Right, same way for solvent we are writing in this form. Now, what happens is chi A plus chi B is equal to 1. We have already studied regarding mole fraction. Right, so now here it is chi A. We can write it in terms of chi B. How we can write? Chi B is equal to 1 minus chi A. Right, so chi A will be equal to 1 minus chi B. Right, so instead of the chi A, can I write this equation? It is 1 minus chi B. So that is what is shown here. I hope it is clear. Now we are going to take the P naught A inside. So you will get P naught A minus P naught A into chi B. You will get like that. Right, now again, what we are doing, this negative sign here, we are going to take it to this side and this PA will be taken to other side. So you will get P naught A chi B is equal to P naught A minus PA. Now we have to get in terms of chi B, right? So now you have the equation here, P naught A chi B is equal to P naught A minus PA. So that is this equation that you are having. Right. Now, in terms of chi B, I have to write chi B is equal to, so this will remain as it is. P naught A, I am going to take it to the other side. So, what you will get? P naught A minus PA divided by P naught A. So, you will get this. Now, you have seen this equation already somewhere. What is this equation? This is relative lowering of vapor pressure, right? So, what can you understand from here? Relative lowering of vapor pressure is also equal to the mole fraction of the solute, right? It is chi B, not chi A, chi B. So, it is mole fraction of the solute. So, you can write all of this together. So, that is P naught A minus PA by P naught A, that is relative lowering of vapor pressure, is equal to the mole fraction of the solute. So, now mole fraction we can also write it in this form. Mole fraction, we know that it is the number of moles of the component divided by the total number of moles. So, chi B means it is number of moles of solute divided by number of moles of solvent plus solute. So, in this format also we can write. So, this is the equation for relative lowering of vapor pressure. This is relative lowering of vapor pressure, which is equal to the mole fraction of the solute, and this is in terms of number of moles. I hope it is clear. So, thus relative lowering of vapor pressure depends only on the number of the solute particles, right? Only in terms of B we are writing, that is, it only depends upon the number of solute particles and it is independent of its identity, that it does not depend upon its nature, only the number of moles. Hence, relative lowering of vapor pressure is a colligative property, right? So, colligative property means it is only supposed to depend upon the number of particles of solute particles, right? Yes. Now, moving on to the calculation of molar mass of a solute using relative lowering of vapor pressure. So, using this particular equation that we have derived now, we are going to calculate or see an equation or derive an equation from which we can calculate the molar mass of the solute. So, you will get questions regarding this. This derivation will not be asked. You need to have an idea about this equation. This equation is important, from which you can calculate the molar mass of the solute, right? So, let us begin with the mole fraction of the solute. Chi B is given as Chi B is equal to NB divided by Na plus Nb. Already we know that that's the equation for mole fraction, right? And from Rolle's law, we already derived this equation, that is a relative lowering of vapor pressure. P naught A minus Pa divided by P naught A is equal to Nb by Na plus Nb. Right, because a relative lowering of vapor pressure is equal to mole fraction, which is equal to this particular equation. So, hence what does it mean? Both of these are equal, right? Now, for a dilute solution, Nb will be very less than Na. Now, what is that? Dilute solution means, very dilute solution means the number of solute particles present is very less. Right, very dilute solution means only very little solute particles will be there. Hence, the number of moles of solute particles will be negligible. Right, so in that case, Nb will be very less than Na. So, from this equation, we can just ignore this Nb, because in dilute solution, the number of moles of B, that is number of moles of solute, will be very less. So, what does that equation become? P naught A minus Pa divided by P naught A. It will be Nb by Na. We are just ignoring this Nb. Right. Now, what is this Nb and Na? Nb means number of moles of solute. So, what is the equation to find out number of moles? It is mass by molar mass. So, number of moles of solute will be mass of solute divided by molar mass of solute. Yes or no? Now, you have number of moles of solvent. That will be mass of solvent divided by molar mass of solvent. Right. So, now what is the equation we are having here? Nb divided by Na. So, what is Nb? Nb divided by Na. What is Nb? Wb divided by Mb. Now, what is Na? Wa divided by Ma. So, what will happen? If we are taking this to the numerator, what will happen? The equation becomes Wb by Mb, and if you are taking into the numerator, what happens? The Ma comes above, right? So, you will get Ma divided by Wa. Yes or no? So, this is the equation that you can see here, Wb into Ma divided by Mb into Wa, which we will get from the equation of number of moles. So, from that, what is that we are finding out here? An equation to calculate the molar mass of the solute. So, you have the Mb here. So, you are just going to rearrange your equation so that you will end up here. So, Mb we are taking to this side, to the numerator. So, this whole part is going to come here, right? So, the equation you are having as of now is P naught A minus Pa divided by P naught A is equal to Wb into Ma divided by Mb into Wa. So, now I need it in terms of Mb. So, I am taking the Mb into this side. So, it becomes Mb is equal to, right. So, already you have this in numerator, that is Wb into Ma, and this in the denominator will come to this side, right. So, it will become numerator. So, you will have your P naught A divided by, now what happens? This part will come here, P naught A minus Pa, and already you have a Wa here. So, this will be your equation. That is what you can see here. So, Mb is Wb into Ma into P naught A divided by Wa into P naught A minus Pa. So, this is the equation to calculate the molar mass of solute based on relative lowering of vapor pressure. So, I hope it is clear. So, here W and Wb are the masses and Mb and Ma are the molar masses of the solute and solvent respectively. So, I hope that is clear. Right. Moving on to the next colligative property, that is elevation in boiling point. Elevation means there will be an increase in boiling point. So, again the same scenario we are going to consider. First, let us consider we have a pure solvent. Okay. That is pure solvent A is considered. So, in that case, boiling point will be there. A specific boiling point will be there. Now, we are adding a non-volatile solute. A solid solute we are going to add. what will happen to the boiling point? Yes, of course, now the boiling point of the solution will be more, right? So that is what we are going to discuss here. So first of all, we need to understand what is boiling point. So boiling point of a liquid is the temperature at which its vapor pressure becomes equal to the external pressure. So that means when will a solution start boiling? When its vapor pressure and the external pressure will become equal. Okay, so the vapor pressure of a solution of a non-volatile solute is less than that of a pure solvent. So what does that mean? The vapor pressure of a solution of a non-volatile solute is less than that of a pure solvent. We have already discussed this. So if I am having a pure solvent A here, now to which I have added another component B, which is a non-volatile solute. Now I have my solution AB here, and this is the pure solvent A. So now will this have more vapor pressure or this will have more vapor pressure? This will be having more vapor pressure, right? Already we have discussed. And this will have less vapor pressure because of the presence of the non-volatile solute. We have already discussed this. So that is what is shown here. The vapor pressure of solution is less. Now once a solution is prepared, after adding the non-volatile solute, the vapor pressure will be less. Therefore, higher temperature is required to make the vapor pressure of the solution equal to the external pressure. Now, what happens? This will easily boil because the vapor pressure is more. But in this case, the vapor pressure is less. So now, already the vapor pressure has become less. So now to make the vapor pressure and the external pressure equal, more amount of boiling point is required. That is why the solution is requiring more boiling point. Hence what is happening? There will be an elevation in boiling point once the non-volatile solute is added. I hope it is clear. Hence the boiling point of the solution is more than that of the pure solvent. The difference in boiling points of the pure solvent and the solution is called elevation in boiling point of the solvent. So the boiling point of this pure solvent and the boiling point of the solution, if we take the difference, that is called as the elevation in boiling point. I hope it is clear. Right. Now let's move on to the equations relating to that. Now let T naught B be the boiling point of the pure solvent and TB be the boiling point of the solution. Right. So the increase in the boiling point will be what? Delta TB is equal to TB minus TB naught. Now why it is TB minus TB naught? TB is that for the boiling point for the solution. It is more, right? Which is more? We have to difference it from there. So TB is the boiling point of the solution minus what was the boiling point of the pure solvent. So that difference will give you delta TB. What is that? Elevation in boiling point. Right. So this delta TB is known as the elevation in boiling point. Now experiments have shown that for dilute solutions, the elevation of boiling point is directly proportional to the molar concentration of the solution. So it's experimentally it was found that this delta TB, that is elevation in boiling point, is directly proportional to the molality. Right. So that means delta TB, that is elevation in boiling point, is directly proportional to molality. Small letter M, molality. Now, to remove this proportionality, we introduce a constant, that is delta TB is equal to KB into M. Now, this KB is the molar elevation constant or ebullioscopic constant. So, it has these names. It is either molar elevation constant or ebullioscopic constant, that is KB. Right. Now, when molality of a solution M is equal to 1, then what happens? Delta TB will be equal to KB, right? If this is equal to 1, what happens? Delta TB will be equal to KB. So, now the SI unit of the constant KB is Kelvin kilogram per mole. Okay. So, I hope till here it is clear. Delta TB is the elevation in boiling point, how much boiling point has increased, and it is directly proportional to molality. The constant we have introduced is called as the ebullioscopic constant or molar elevation constant. Right. Now, let us see the graph here. You can see this is a vapor pressure and temperature graph. Okay. Vapor pressure versus temperature graph. So, here you can see this is for the solvent and this is for the solution. So, this is for the pure solvent. At this point is the point wherein the boiling takes place. That is, the vapor pressure of the solvent and the external vapor pressure becomes equal. Now what happens? Once the non-volatile solute is added, it will increase to this point. That is, this is for the solution. So there is an increase in what? Boiling point. So this difference you can see. Yes, this difference you can see, that is your delta TB. So this point in temperature, that is the boiling point of the pure solvent, and this point at temperature, that is the elevated boiling point of the solution. So this difference will give you the elevation in boiling point, right? So now moving on to the calculation of molar mass of solute using elevation in boiling point. So likewise we have done in a relative lowering of vapor pressure as well. That is related to the vapor pressure. Now we are relating it to the boiling points. Alright. So let's see. Let W be the mass of the solute of molecular mass Mb dissolved in WA gram of the solvent, then molality of the solution is given by the equation. So already we know that what is molality? It is number of moles of solute present in 1 kilogram of the solvent, right? So what is the equation for molality? We have already studied this. Number of moles of solute divided by the mass of the solvent, right? Mass of the solvent. Now Nb, how you can write? Nb is Wb by Mb, and already you have a Wa here. Right. So this is the equation, and if Wa is in grams, we use 1000 as well. So that is the equation that is given here. So this is the equation for molality which we have already studied. Now substituting the values of M in this equation. So now what we are going to do? We are going to substitute the value of M in which equation? Delta Tb is equal to Kb into M. This is the equation for elevation and boiling point, right? So now instead of this M, we are going to substitute this particular equation. So you'll have delta Tb is equal to Kb into M. In that M part, we are going to substitute Wb into 1000 divided by Mb into Wa. So molar mass of the solute is calculated using the equation. So what we are going to do? We are going to just rearrange this. We'll take this Mb here and this delta Tb will come here. That's it, right? So Mb will be equal to, that is molar mass of solute is equal to the ebullioscopic constant into the mass of the solute into 1000 divided by delta Tb, that is elevation in boiling point, into mass of solvent. So this is a very, very important equation to remember, how you can calculate molar mass using the elevation in boiling point concept, this colligative property. I hope it is clear. Moving on to the next one, that is depression in freezing point. So again the same condition we are going to take, that is a pure solvent is present. Once we add the non-volatile solute, now what is going to happen to the freezing point? So there will be a depression in freezing point. That means a freezing point of the solution will be lesser than that of the pure solvent, right? So what is freezing point first? Freezing point of a liquid is a temperature at which vapor pressure of the solvent in its liquid and solid phase, right? In liquid and its solid phase become equal. Now as we know that vapor pressure of solution containing non-volatile solute is lower than that of the pure solvent. Already we know that the pure solvent will have more vapor pressure and the solution will have lesser vapor pressure. Now this decrease in freezing point of liquid is known as depression in freezing point. So because of that, what happens? Now once you have the solution, that is A and B is present, right? Non-volatile solute also we have added. We have AB, that is your solution. What will happen? The vapor pressure is less. Now what happens? The freezing point will be lesser than that of the pure solvent, right? So now let us discuss the equations regarding it. Depression in freezing point, the same way, it's quite similar to the elevation in boiling point. The equation is quite similar. So the depression in freezing point delta Tf will be Tf naught minus Tf. Now why it is Tf naught minus Tf? Yes, the pure solvent is having more freezing point than the solution. So we write Tf naught first minus Tf. But in the case of boiling point, elevation in boiling point, it was Tb minus Tb naught. Okay, so you have to remember that. Experiments have shown that for dilute solutions, depression in freezing point is directly proportional to the molality. Again, like in case of elevation and boiling point. So you have delta Tf is equal to Kf into M. That is, here also the depression in freezing point is directly proportional to the molality. So to remove the proportionality, so the constant we are introducing here is called as Kf, and it is called as a molar depression constant, or else it is called as a cryoscopic constant. Okay, and when molality of solution is 1, then delta Tf will be equal to Kf. From this equation itself we can say. Here also the unit is Kelvin, kilogram per mole. So here in the graph you can see vapor pressure versus temperature graph again. So for the pure solvent you can see the temperature at which it freezes is T naught F. Right, you have this, and for the solution you can find it, it will be here. So this is your Tf. So this difference will give you delta Tf, which is the depression in freezing point. Right, so now let's calculate the equation to find out the molar mass of solute using the depression and freezing point. So let's see. Here also, the equation for molality we already know, WB into 1000 divided by MA into WA. Now, we are going to substitute this M value in this particular equation, that is delta TF is equal to KF into M. So, in this place of M, we are going to substitute this equation. So, you have delta TF is equal to KF into WB into 1000 divided by MB into WA. So, now again, we are going to just rearrange this. MB will come here, delta TF will come here. You will get this particular equation. This is the equation to calculate the molar mass of the solute using depression and freezing point. So, I hope this is clear. So, this and the equation for elevation and boiling point, it is quite similar. It is just the change in boiling point and freezing point equations. So, I hope this is clear. This is also a very important equation. So, in the next class, we are going to study the next colligative property, that is osmotic pressure. Before that, we have to study what is osmosis and then what is reverse osmosis, and the last topic, that is abnormal molar mass. So, I hope the concepts that I have covered in this session is clear for you. So, that's all for today. Thank you.